Algebra 1, how we doing? Mr. Bivens here. We're going to start off with this study guide. I thought I'd make a video for this for y'all so that y'all can just, again, have more exposure to different topics. And so we've got 14 topics here. Excuse me. Some of y'all completed this for a quick reward. Thank you to those of you that did. Those of you who didn't, that's A-okay. You're still going to do great. Hope y'all pay attention and you can get something out of this, okay? So we got 14 topics, starting with the real number system. So something fun I did was I had AI, I sent AI this PDF, and I had it develop me different quotes from different people for each of these 14 topics. And so starting off with the real number system, ChatGPT gave me a quote from Miss Pearl Buck, and it says, "Order is the shape upon which beauty depends." And their reasoning being, real numbers bring order to chaos in math. And so starting off strong with the real numbers, these are just going to be all numbers, okay? All numbers. And if you want the actual math lingo, it looks like an R, just like that. The real number system. These are all the numbers we currently have. When you get to Algebra 2, you'll learn about imaginary numbers. Yes, you heard me right. Imaginary numbers, they do have a purpose. But for now, all the numbers we know, we're going to call real numbers. Some examples of irrational numbers, you can think like the letter E. You can think like pi, square root of just about any numbers. Fun fact, square root of any prime number is always going to be irrational. So square root of 43, for example, would be irrational. Or decimals that don't end and don't have a pattern, okay? So, for example, the square root of 43, okay? Looking at rational numbers, our symbol for that is a Q. These are your fractions, your decimals. So, for example, 5 and 7/6, 5.2, 1/2, maybe 0.5 repeating, all those fraction decimals. Integers, these are our counting numbers. Again, we have this little cool Z thing. That's our symbolic symbol notation for the set of integers. These are all of your positive and negative numbers. So like negative, wrong tool there. -3, -2, -1. It includes 0, 1, 2, 3, so on and so forth. Whole numbers, same thing as the integers, just get rid of get rid of the negative numbers and not 0. So we're going to start at 0, we'll go 1, 2, 3, all the way up to positive infinity, okay? Natural numbers, similar to whole numbers, they just does not include 0. So 1, 2, 3, Those are our sets of numbers. So for example, let's do 1 and 4, okay? If I give you a number, tell me which number it belongs to. So I'm looking at 1 and 5/7. Is it a natural? I'm just going to go from the bottom to the top. Let's see what sets this belongs to, okay? Is it a natural number? No, natural numbers do not include fractions, so it can't be a natural number. Is it a whole number? Not looking like it. Not looking like it. Is it an integer? Nope, I wish. Is it a rational number? Of course, this is a rational number. This 1 and 5/7 tells me that's a fraction. That decimal does repeat. And so it does not go on forever. So thus, I'm going to say it's at least a part of the set of rational numbers, which we go by a fancy Q. You don't have to write it like that. And then it also belongs to the set of real numbers. Okay, if it belongs to this rational numbers, it must belong to real numbers. So for example, if you give me the number 1, well, 1 is a natural number, it's a whole number, it's an integer, it's rational, and it's real. Okay, so it's just part of all of those. And then lastly, let's do number 4 here, pi minus pi. Well, we need to ask ourselves, what does that actually evaluate to? Well, the same number minus the same number should give me 0, right? And so now I ask myself the question, what all sets does the number 0 belong to? Is it a natural number? No, the set of natural numbers does not include 0, but the whole numbers do, the integers do, rational numbers do, and real numbers do. Okay, so again, if it belongs to the set of whole numbers, it belongs to all the sets above. Obviously not irrational, okay? So hopefully we put whole, set of integers, rationals, and reals. Belong to all of those, okay? Topic number 2, moving on, we have our properties. I'm about to sneeze here, excuse me. Maybe not. Never mind, we definitely did sneeze. Topic number 2, we got properties. These are our properties in math. We use these quite a bit. And the quote I have for properties is from some random person named Rumi, and it says this: life is a balance of holding on and letting go. And so these properties are the laws that keep math balanced and harmonious, some would even say. And so let's begin our talk of topic number 2, properties, with the property of commutativity, or the commutative property. Here's what it says. It says that some number plus another number has to be equal to that other number plus the original number. Okay, this is all talking about order, the order in which you add. Or we can have the same thing, but for multiplication, the order in which we multiply. A times B, again, just two numbers, must be the same as B times A. We can add or multiply in any order. Commutative property. The identity. We have identities for the operations of addition and multiplication. And so, for example, the addition identity, if we have some number A, what do we add to it to give us back A? We're going to add 0. So A plus 0 has to be the same thing as A. Same thing for multiplication. Some number times what is going to give us A. In that case, we multiply any number by 1. It should give us itself back, in that case A. Okay. Next property, zero product property. This just says any number times 0 has to be 0. And it also tells us that the sum of any two numbers times 0 must be 0. Okay. Pretty self-explanatory. Reflexive property. This shows up a lot in honors geometry. So those of you that will move on to geometry, you will see this property used in proofs quite a bit. And it honestly feels like something that's super simple. All it is that obviously some number is equal to itself. And then the example that we have, for example, I could say that, well, 15 has to be equal to 15. Okay. Doesn't seem like we'd ever need that, but it turns out we actually will need that to prove some things when we get to geometry. Okay. Associative property, this is about how we group different things. And so for addition, here's what we're going to say. We take two numbers and add them together, and then we add the third number in. We can say with certainty that that is the exact same thing as taking your first number and adding it to the sum of your last two numbers. Okay, does not matter what order we add in, and we get that associative property is kind of a branch of the commutative property. Multiplication looks similar. We take two numbers, multiply them together, A, B. If we multiply it by C, we can conclude that is the exact same thing as A times the product of B and C. And again, A, B, and C are just three different numbers. Inverse property, this one's pretty important. This says, well, what two things can we add or multiply together to get our identity? And so in this case, our identity for addition was the number 0, and for multiplication it was 1. So I'm going to ask myself the question, what two things when I add together will always give me 0? So if I have some number A, what can I add to A to get 0? Well, I can add negative A. In this case, just subtract A, and I'm going to get 0. When thinking about multiplying, I have some number A. Well, what can I multiply by A to give me 1, our identity element? Well, A times 1 over A is going to give me 1, and that's it. Next up, this property y'all are very familiar with. This is a distributive property, and this is if we have some number A being multiplied to the sum of B and C, to some number being multiplied to two other numbers, we can use the distributive property, which we're all pretty familiar with, to actually take that A and multiply it by each element inside the parentheses. So this is going to be AB plus AC. Next up, I'm going to go ahead and skip the example for that. The symmetric property. This also shows up quite a bit in geometry, and it just says, if we have two numbers, A and B, and they're equal, then we can conclude that B is equal to A. So just the opposite. This is similar to the commutative property. It's very similar to the commutative property. Okay. Lastly, we have the transitive property. This is one that a lot of y'all were confused upon. Again, it shows up quite frequently in geometry. Reflexive, symmetric, and transitive properties we talk about at least 4 or 5 different times in different contexts in geometry. And so these are very crucial to know now, so that when we see it again in geometry, it's not something brand new, okay? Here's transitive property. If I have one number, A, and it's equal to number B, and that same number B is equal to some number C, what do you think we can conclude? Well, we can conclude that A is equal to C, okay? Simple as that. And so now, given this host of problems, can we identify the property that's being used? Starting off strong, I'll do the ones on the left side here. Starting off strong, I see two things being multiplied together and giving me 1. So I see the multiplication, I see a 1. I know 1 is the identity element for the order of multiplication, for the operation multiplication. And I see that these two things that are being multiplied are indeed reciprocals. And so I'm going to say this is the inverse property. Inverse property would be the correct property, and technically it is of multiplication. We also have an inverse of addition, so we need to be careful there. Okay, number 9. If 3m is equal to negative 21, then negative 21 is equal to 3m. This looks like something we see a lot in geometry, which is going to be the symmetric property, which just says if A is equal to B, then B is equal to A. The order does not matter. Next up, if 2q plus 1 equals 9 and 9 equals 81, then 2q plus 1 equals 81. So what I'm saying is if something is equal to something else, and that something else is equal to something else, well, then I can probably include that first something as equal to that last something. That's going to be the transitive property, which also shows up quite a bit in geometry. And of course, it shows up in algebra too, but its primary use is in geometry. And then if you ever take higher college math, you'll see these used for more formal proofs, okay? This next one, let's take a look here. 2p times 3q is equal to times negative r is equal to 2p. This is the associative property. This is just a different order of multiplication. And so this is just the associative property. And you could put of multiplication because that's what's being used here. Lastly, 6y plus 30 is equal to 2 times the parentheses 3y plus 15. Let's see. It looks like they just use a distributive property to distribute this to both of the elements inside the parentheses. And so this is just going to be the distributive property. Okay, that was topic number 2, which was all about the properties. Okay, moving on to topic number 3, evaluating expressions, both numerical and algebraic. The quote I have here is from Lao Tzu, and it says this: "A journey of 1,000 miles begins with a single step." And I think Lao said that primarily because all of these math problems start with starting the first step of the problem correctly. You know, if you mess up one of the things early on, your problems, as the further you go down, your answer is already wrong, okay? For this, let's see. This 19 looks fun. I'll do number 19. I'll do number 22. And I'll do number 18. So, this we need to keep in mind PEMDAS. So I'm going to put a little star EMDAS for PEMDAS. This is really what this is testing. Can you evaluate expressions using PEMDAS? And also, can you evaluate expressions by plugging in values that they give you? So starting off with this first one, I see, let's focus on the numerator first and then move to the denominator. So 7 plus the absolute value, negative 8 minus negative 5 squared. So that 5 squared evaluates to a 25 exponent first, and that's being subtracted from negative 8. Well, that entire thing evaluates to negative 25 minus 28 is a negative 33. And the absolute value of negative 33 is positive 33. And then 7 plus positive 33 is going to give me a positive 40 on top. Let's figure out what's on the bottom. We have a parenthesis. What is 1 minus 4? Well, that's negative 3. What is negative 3 cubed plus 17? Well, negative 3 cubed is negative 3 times negative 3 is a positive 9. Positive 9 times negative 3 is a negative 27. And I add that to 17, and I'm going to get a negative 10. What is 40 divided by negative 10? Well, that's negative 4. And we are done. Okay. Number 19, this test, can you evaluate an expression? They're going to give me values of P and Q, and they say, evaluate this. Okay, so let's just start up from left to right. 5 times P squared. What is P? P is negative 4. I'm going to zoom in here too, so you get a better look. Negative 4 squared, and that's being multiplied by negative 2. And then I'm subtracting from that 7 times Q. Well, what is Q? They tell me Q is negative 2, right here. Okay. From there, we are still going to use PEMDAS. And so the first thing I do see a lot of parentheses, but most of them are being multiplied. So the only real thing we're going to do here first is evaluate this negative 4 squared, okay? Negative 4 squared is going to be a positive 16. So I have 5 times 16 times negative 2 minus 7 times negative 2. From there, I'm going to multiply everything left to right. When I multiply 5 times negative 2, I get negative 10. Negative 10 times 16 becomes negative 160. And then negative 7 times a negative 2 should be a positive 14. Add those together, you get negative 146. Okay. Lastly, number 22, they throw in some more absolute value. Hopefully, our main thing here is we need to be careful that when we plug this negative 2 into D, we're putting parentheses around that. That's pretty much it, okay? So let's, again, just go left to right, still following PEMDAS. So we have the absolute value of 3 squared minus, what's my value of D? They tell me it's negative 2 to the 4th absolute value plus parentheses CD squared. Well, what's C times D? That's a negative 6 squared. Okay, I'm going to go and do that quick math right there. On the left, I have 3 squared. Well, that evaluates to 9. Before we do that, we probably want to go and evaluate negative 2 to the 4th because PEMDAS. And so negative 2 to the 4th, negative 2, positive 4, negative 8, positive 16, but there's a minus sign here, so this becomes 16. 3 squared is 9, still being added to negative 6 squared. What is 9 minus 16? Well, it's negative 7. And let's go and do this. Negative 6 squared is positive 36. What is 7 plus 36? Well, that's a positive 43. We're done. Also, apologies for the sniffles. I have not been feeling the best, but a little congested, some would say. So bear with me if I sound like a sick old hag. Apologies. Topic number 4, can you translate expressions, equations, and inequalities? This one, I think, is a really good quote by Anthony Burgess, or Burgess. Apologies if I said that wrong, Anthony. It goes like this. Translation is not a matter of words only. It is a matter of making intelligible a whole culture. You know, in math, we translate expressions, and we think that's like learning a universal language, and that language being math. Very beautiful quote by Anthony. There's my AC that just turned on, keeping the room nice and cold. We can do, we'll do a couple of these. Let's see, I'll start with number 23. The sum of twice a number and 9 is 25. Well, the sum of twice a number and 9, that's 2 times some number. I'll use x plus 9 and has to be equal to negative 25. And that looks about it to me. 2 times number plus 9 is negative 25. Okay. 10 less than the quotient of a number and 3 is 8. So the quotient of a number and 3, I'll call that x over 3. 10 less than that must be equal to 8. Boom, boom, boom. Hopefully these aren't too bad. Number 25, 4 times the difference of a number and 7. So 4 times the difference of some number and 7 is at least negative 52. So if something is at least a number, it must be bigger than or equal to that number. So it should be greater than or equal to negative 52. Very good. Last one, 26. 15 subtracted from the product of a number and negative 4 is at most 32. So 15 subtracted from the product of a number. So the product of a number and negative 4 is probably negative 4x. And 15 subtracted from that is at most 32. I see that at most. It means it cannot be bigger than 32. So I know that 32 has to be bigger than or equal to all of that. Or you could read that as less than 32. Either one. Very good. Topic 5 out of 14. Y'all are making pretty good progress. Hope the studying hasn't been too stressful. So y'all should be thankful that your exam is multiple choice. You know, I didn't want to be as kind of mean as I was to geometry, but you know, it's only 62 questions. So, and if you can do the study guide, you are more than prepared for the semester exam. Just throw that out there. Topic number 5, solving equations. I've got a quote here from Travis Kalanick. It says, "Every problem has a solution, but you just have to be creative enough to find it." And so a lot of these problems solving the equations is actually finding the beauty in the solutions that keep the scales balanced in math. And so this is a skill that will show up for the rest of your mathematical career. Depending on the field you go into, this is probably one of the most foundational skills you can have. Engineering, being a doctor, learning chemistry, learning biology, whatever. Solving equations, it won't leave you. And so this is a skill you need to have mastered. Let's start with something simple like number 27. We'll go to 27, we'll go to 30, and then we'll go over to 32. Okay. So 27, starting off strong, our goal is to always isolate our variable. And to do that, we are going to use what I like to think of as reverse PEMDAS. So take PEMDAS and do the opposite first. So can I add or subtract? Of course we can. Let's subtract 11 from both sides. When I do that, the 11s go away. Negative 45 minus a negative 11 is a negative 56, and that's equal to negative 4x. Next up on PEMDAS, can I do anything? Add and subtract? Nope. Can I divide or multiply? I can. Negative 4 is being multiplied, so let's divide it. Negative 4, boom, boom. I get x is equal to a positive 14. The negatives cancel out. Positive 14. Very good. And we can check our work by actually plugging this value back into x. Okay, I'm not going to do that for sake of time. I know it's right. But if you're not sure, you can always check your work. Okay. Number 30. Take this problem. I like to distribute everything first, so I'm going to do that. 19 minus 6w plus 10 is equal to 15. Let's now combine like terms. I have a 19 and a positive 10. Let's combine those. So I have a negative 6w plus 29 is equal to 15. Subtract 29 from both sides. Boom, boom. That goes away forever. See you later. I'm left with negative 6w is equal to a negative 14, I believe. Let's divide both sides by negative 6. And I should be left with w is equal to negative 14 over negative 6 becomes a positive 14 over 6. Divide both by 2, I should get 7 over 3. Should be pretty good. Okay. Continuing on, number 32. Again, let's just distribute everything, and I'm actually going to erase some of my work from above. Apologies. Here we go. Okay, 6 minus 12p plus 8 is equal to 6 minus 12p minus 1. Let's go ahead and combine like terms. When I do that, I'm going to get negative 12p plus 14. And that's going to be equal to negative 12p plus 5. Already, this is not going to work out nice because when I add 12p to both sides, what we're going to get is that 14 equals 5. And I don't know about y'all, but 14 definitely does not equal 5. And so we're going to say there is no solution to this equation. And we usually denote that by a little 0 with a circle through it. Okay, no solution. 14 does not ever equal 5 in the set of real numbers. Okay, different problem, different question. Let's do 34. This is a good skill to have. This shows up a lot. We have the quotient of two things being set equal to each other. We typically do what? Great answer. We're going to cross multiply. And so let's actually cross multiply both of these. And so starting with 2 times x minus 1 has to be equal to 4 times x plus 8. Make sure you take whatever term and you multiply by the entire term. You can't just multiply it by 4 times the first term. It's a very common misconception. Let's distribute out and solve for x. So 2x minus 2 is equal to 4x plus 32. Let's go ahead and add 2 to both sides. Boom, boom. I have 2x is equal to 4x plus 34. Subtract 4x. Get all the x's on one side. Boom, boom. Negative 2x is equal to positive 34. Let's divide by negative 2, and then we're done. When I do that, I get x equals negative 17. Okay. What we do to one side, we have to do the other. All right, move on. Let's do number 35. Solve this equation, c equals 2 pi r, for r. This looks to be the circumference of a circle. C being the circumference is equal to 2 pi r. That's a formula we have. And so they say we'll solve this for r. So in order to get r by itself, it's being multiplied by 2 and by pi. So let's divide by 2 pi. Once we do that, I'm left with r is equal to c over 2 pi and r is indeed by itself, aka solved for r. There we go, very good. Again, y'all can do most of these. This will definitely show up on the semester exam. This was the topic of literal equations. This is very physics heavy. When I took my university physics class, which was calculus-based physics at Ouachita, it was a lot of manipulating equations or solving equations for different variables. And so learning this skill now is just a giant jump start for if you'd go to take AP Cali B, BC, up in the high school, upper school, or maybe you take physics, whatever, who knows. Very foundational skill. Next, we move to graphing and solving inequalities. And a great quote I have for this, it's actually by an unknown source. Nobody knows who said this. I'm going to claim it for myself now, if that's okay with y'all. It says this: life is not always about making the right choices. It's about making the most of the choices you have. And they say that because inequalities remind us that there isn't just one solution. Sometimes there's many solutions to these problems, okay? Very beautiful quote by Mr. Bivens there. So how do we solve these inequalities? Let's actually figure it out. So we're going to treat these just like we treat regular equations, but the difference is we got a different sign and we have some small things to do with these signs if we're in a certain situation. That's pretty much it, okay? So let's start with number 39. Again, we're going to solve this for x, and so let's go ahead and add 14 to both sides. I'm left with 3x is less than or equal to negative 3. Let's divide both sides by a positive 3. I'm left with x must be less than or equal to negative 1. So let's put a dot on negative 1. And since I see this equal to sign, it is going to be a closed dot on negative 1, meaning it includes that value, aka it's equal to it. And if x is less than negative 1, all the numbers to the left of negative 1 are going to work. So we draw a nice little arrow going to the left. And we're done, okay? Any questions? Sounds good. Let's move over to number 43. This is an inequality joined by the word or. We call this a compound inequality because it's in two separate inequalities. And so we're going to solve both of them separately, okay? Just like what we did earlier, but we're going to solve them separately. So solving this first side, this side right here, for x, we add 4 to both sides. When I do that, I get x must be bigger than 7. And I'm going to hold off on graphing that just for half a second. I'm going to draw a little line here. And then to solve the other one, let's subtract 1. I get 2x is less than or equal to negative 4. Let's divide by 2. I get x is less than or equal to negative 2. So x has to be greater than 7, or x has to be less than or equal to negative 2. And so for or inequalities, or compound inequalities, I know that both my arrows are going to be going opposite directions. There's not going to be any real overlap, and there's going to be some numbers that actually won't even work for this. So let's start by graphing. X is greater than 7, so I go to the point 7, and I'm actually going to put an open circle. Think for a moment, why would I put an open circle there? Good, yeah, I don't see an equal to sign, so I'm going to put an open circle. And if x is bigger than 7, is my arrow going to go to the left or to the right? Yeah, it's going to go to the right. All the numbers to the right of 7 are indeed bigger than 7, okay? So those numbers, x must be bigger. Next up, x is less than or equal to negative 2. Let's put a circle on negative 2. Is it going to be an open or a closed circle? Yeah, it's going to be a closed circle. Very good. There's a line here, which means it's equal to negative 2, which means I'm going to have a closed circle. And is my arrow going to go to the left or the right? Very good. It's going to go to the left because if x is less than negative 2, that means that all the numbers to the left of negative 2 are indeed less than negative 2. And I just dropped my Apple Pencil. Okay, there we go. Picking back up. Let's get it quick. Let's see how much battery we're at. 94%. We are golden. Okay. Let's solve an and compound inequality. Let's do number 45. I'll zoom in on this one too, so I have more space to write. To solve an and compound inequality, meaning I don't see the word or, and there's a bunch of weird stuff going on here, we have some stuff in the middle, and our goal is to get whatever's variable is, in this case a w, we want to get that by itself. And so we're going to use the same idea as solving equations, as solving inequalities, but what we do to the middle, we're going to do to both sides of our inequality. So to both this side and this side. So let's start by adding 1. And I'm going to add 1 to 11 and to negative 21. Okay. So negative 21 plus 1 is a negative 20, which is less than or equal to 4w, which is less than 12. Let's divide by 4. And we're going to, again, do it on both sides. Divide by 4. Boom, boom. I get negative 5 is less than or equal to w is less than 3. With and inequalities and compound inequalities, they look like dumbbells. And so I just literally look at my two numbers. I look at the signs, and I plot. So negative 5, there's a negative 5 is less than or equal to w. So I'm going to go negative 5, put a closed dot because there's an equal to sign. And I'm going to go to positive 3 and put an open circle because there is no equal to sign on this right there. And we connect them. All of the values between negative 5 and 3 are going to work. And it will solve this inequality. Okay, and that is it. That is it. Now we move to topic 7, relations and functions, arguably one of the most important skills of the first semester of Algebra 1. And again, the quote I have for this is by an unknown source, but I'm also going to claim this for myself. And here's what it says. Your relationships are only as strong as the foundation you build them on. Relations and functions build a foundation of how inputs and outputs connect, okay? And so for every input, we have an output. Every x value, we have a y value. If so, it's a function, okay? And so let's look through most of these because I believe this is where y'all need the most help. And so let's talk about first number 47, and let's go over the domain, the range, and ask the question, is it a function, yes or no? So for number 47, the domain, we're going to write in set notation. Let's just all of my x values, so I have a negative 4, 0, 4, and 8. We typically write them from smallest to leastest. That doesn't make any sense. Smallest to greatest or least to greatest. And so my smallest x value is negative 4. My next smallest is a 0. My next smallest is a 4. And my next smallest is an 8. And so that is the set of the domain. And then all of these also have a corresponding output or y value. 2, negative 1, negative 1, and 2. Here's our range. I am going to simplify all of these. I see, again, we're writing this from least to greatest, but I see negative 1 twice, so I'm only going to write that once. And then I see positive 2 twice, I'm only going to write that once. We're done, okay? Is it a function? This is a function, yes, because none of the x values repeat. They are all different x values. So, for example, there's an 8, a 4, a 0, and a negative 4. None of those are equal to each other, so it is a function. Next up, 48, they give us a table. They say find the domain, range, and the function. For the domain, I'm looking at my x values. For the range, I'm looking at my y values. So I'm going to go over this pretty quick. We have negative 1, 2, 7. For the range, we should have negative 2, negative 4, negative 3, negative 2, positive 9. And it is not a function. Why? Well, because negative 1 repeats twice. Ain't no way that's a function. I'm going to skip 49. Again, you can just pick out all these points and get x and y values. Make your conclusion. This one will be a function in case you're curious. But yeah, you can do that one if you'd like. I really want to hit on 50 and 51. Writing domain and range for these, y'all have had problems with, and so I'm going to take some extra time to kind of talk about these because I think it's beneficial to know. So domain. To find the domain of a function, if they give it to me graphically, I'm scanning from left to right. What numbers do and do not work. So for example, I see 2 arrows, meaning this goes down on forever. And so I can conclude that every single value as I go from left to right, whatever, however you scan, all numbers are going to work. And so we're going to say R, or all real numbers. Either one of those will work. This just means the set of real numbers, which is the exact same thing as all real numbers, okay? The range, though, not every single number works. And so as range, we're going to scan from bottom to top. So as I scan, again, from down here, I'm scanning. Uh-oh. Something happens right here, okay? Let's see what that value is at 1, 2, 3, 4. So at y equals 4, everything above that, there's not a graph. Like no function actually exists there. And so my only values that are in my range are all the numbers that are less than or equal to 4. Do we see that? So here's y equals 4, y equals 3 works. I've got 2 values. Y equals 2 works, y equals 1 works, y equals 0 works. All the way down forever is always going to work. But above 4, Here's the point y equals 4, and there's no values. Question mark, question mark. And so we actually write that using interval notation. Not interval notation, using inequalities. You could write it as an interval if you wanted to. It'd be like this. Bracket, nope, it'd be parenthesis, negative infinity, comma, 4 bracket. Either one of those work. I think this is easier. Do what you want. Is it a function? Sure, it passes the vertical line test. So if I were to take my pencil and just place it on all these lines, do I touch in 2 points? And pretend these red lines are my pencil. Does it only touch my function or my graph at exactly 1 point? Yes, it does. So it what we call passes the vertical line test. We're chilling. Number 51, this one's a little complicated. Again, domain, we scan left to right. What's the farthest left x value that will work? Well, that's 0. And what's the biggest number that's going to work? Well, 1, 2, 3, 4, 5. X equals 5 is my biggest. Do all the numbers in between those work? Sure. So I'm going to write a compound and an equality statement that looks like this. And all this reads is x is between 0 and 5. So x is bigger than 0, as we can see from this inequality, and x is less than or equal to 5. How do I know it's equal to? Well, if it wasn't, they would put an open dot. They would put an open hole in the graph, but they don't. So we're going to assume it's equal to. Same thing for the range. I scan bottom to top. What's the smallest y value that I see? -2. Here it is. This is the smallest y value I see. What's the biggest? +3. So all the numbers between -2 and +3 are going to work. And again, we're in y. Some of you on your exams put an x here. We're in range world, so we're definitely dealing with the y's, our outputs. And so all the numbers between that should work. So just like this, okay? If you're not sure, you can read them separately. Does y have to be bigger than or equal to -2? Sure, bigger than or equal to -2. And is it less than or equal to 3? Sure. And so all of these 5 points are going to work. Is this a function? No shot. If I draw a line, it touches in 2 points. Boom, boom. Not a function. Fails the vertical line test. I'm going to put nah. See you later, bro. And again, on this, we have evaluating functions. This also is something that shows up quite a bit. And so I'm going to do, let's see here. I'll do 53, 55, and 54. 52 is pretty easy. We'll start at number 53. If they give us some function and they tell us it's equal to 2x squared plus 3x minus 19, and they say find f of 4, okay? So there's f of x. F of 4 will be the same thing as 2 times plugging in a 4 everywhere I see x. 3 times 4 minus 19. And you can plug this in your calculator. You can do the math. 2 times 16, 4 squared 16 is 32. Let's see, we have... Oh, wait, it was a -4. Never mind. I'm not very smart. Still is a positive 32. It's going to be minus 12, minus 19. That should give you a 1 when you're done with it, all said and done. So you should just get a 1 there. Okay, just plug in -4 into the function and then simplify. PEMDAS does still apply. Next up, they give us another function. In this case, it's x squared minus 6x. They say find the range. I think range say find the y values. If the domain is this, domain is our x, they give us x values. They say find the y values. So let's first find f of -7. Well, I just plug in -7, and -7 squared minus 6 times -7 is the exact same thing as -7 squared is a positive 49. -6 times -7. Ooh, that's a tough one. 6 times 7 is going to be 42. So plus 42, that should be a 91. Boom, chicka boom. Okay. Moving on, we need to find, so that's f of, it's -7 done. Let's find f of -2. So again, I'm just going to plug -2 directly into my function. Okay, so let's do that now. -2 squared minus 6 times -2. -2 squared is a positive 4, and then -6 times -2 is a positive 12. 4 plus 12 is indeed 16. Okay, we're chilling. We're done. And that does not look like a 16. That does. There we go. All right, lastly, f of 1. This is going to be equal to 1 squared, which is 1, minus 6 times 1, which is 6. This should be a negative 5. And so our range is going to be equal to the set, and then we just take our numbers, boom, 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 90, oh, wait, right, at least the greatest, almost forgot that, negative 5, 16, 91. And there's our final answer, okay? Very good. All right, 55, given the graph of some function, here is the function, find f of 2. This is an x value, so find x equals 2, and then it's asking the question, what's your y value? Well, at x equals 2, which is right here, my y value is 1, 2, 3, 4, negative 4. F of 2 is equal to negative 4. Boom, chicka boom, we're done. Okay. Next up, topic 8, zeros, arguably one of the most important topics. This is what you do in all of algebra. Most of calculus is find zeros of functions. This is another foundational skill. A lot of these are pretty foundational skills in Algebra 1. And the quote here I've got is from our boy Tom Stoppard. Never heard of that. And here's what he says. He says that every exit is an entry somewhere else. Ooh, that's good. That's deep. That's phenomenal math lingo. And we think about that in context. Again, every exit is an entry somewhere else. Zeros represent the turning point, where functions cross into new territory. Love it. What are some other words for zeros? We have roots, we have solutions, and we have x-intercepts. Intercepts. Can't really spell. Not an English teacher. To find the zeros of a function, we want to know where the entire thing equals 0. AKA, where do I intercept the x-axis? AKA, where is my y value 0? I know that example on number 56, f of x, where is that equal to 0? So I plug it in for 0, and I get 0 equals 4x minus plus 12. Can't read, right? Again, solve for x, find where it equals 0. So let's subtract 12 on both sides. I get negative 12 is equal to 4x, divide by 4, boom. X equals negative 3 is a 0 of this function, is what we say, okay? X equals negative 3 is a 0. Y'all can do the same thing with 57. Let's actually do number 58. Let's use our calculators to find the zeros here. Okay, so I'm actually going to... After a brief reset of our screen recorder, we are over to a calculator, which is similar to ones that hopefully y'all will be using on your semester exam, depending on if I let y'all or not. Leaning towards yes, no promises yet. But... Again, we're on number 58, and it was asking us to use our calculator to find zeros. And the function they gave us was x squared minus 5x minus 14. And they said find the zeros. And so we cannot solve that algebraically. We don't have little tools to actually solve that yet. What we would do is we would set f of x equal to 0 and do some cool math magic. But we learn that next semester. And so right now we use our calculators. The first thing I'm going to do is I'm actually going to hit y equals. It's going to bring up this. And this actually lets me put in a graph. And so I'm going to type in x squared minus 5x minus 14. And I'm going to hit graph. And so when I do that, it's going to spin me on a graph, and I can just count. And so it looks like one of them is at negative 2. That's 1, 0. AKA where I cross the x-axis. And the other is at x equals 1, 2, 3, 4, 5, 6, 7, 8. I think that's a 7. 1, 2, 3, 4, 5. Yeah, so negative 2 and 7 are both of our zeros. And so we can say that x equals parentheses negative 2, comma 7. Those are my zeros, and we're done, okay? Same thing with number 59. You would just throw that in a calculator and see where it crosses the x and y axis. Topic number 9, we've got some slope. This is the heart of calculus, some would say. And so the best quote I could find that AI made me for this was of Abraham Lincoln, funny enough. And here's what Lincoln says. He says, the best way to predict your future is to create it. And if you think about it, slope determines the future direction of your line, just like your choices shape the paths you take. Very inspirational. But given a graph, here's what we're going to do. We're going to use our rise over run. Okay, so on a graph, we just count how far up we go, and then we see how far left or right we go. Rise over run. If they give us a coordinate, AK ordered pairs, we can use our handy-dandy formula. M equals y2 minus y1 over x2 minus x1. this isn't drilled into your mind yet, it should be, okay? Starting on, for example, number 60, we go up 1, 2, 3, 4, 5, 6, up 6, and over 1, 2, 3, 4, over 4. Simplify that, we should get 3 over 2. That's our slope, up 3 over 2. 62, every single vertical line has an undefined slope. Every single horizontal line has a slope of 0. So those are those two, okay? 64, I'll pick this one. They give me 2 coordinates. Let's see, here's my y2, here's my y1. -3 minus -1 over x2. Here's my x2, here's my x1, over x2 minus x1. -4 minus 2, okay? When I have that, this becomes a plus. -3 plus 1 becomes a -2. -4 minus 2 over -6. That simplifies to a positive 1/3. We're done, okay? Same for 65 and 66. This, again, shows up in every other single math class you ever take. So, hope you know it. Hope you know it. It's not too bad. Topic number 10, can you graph linear equations? The quote I have for this is actually by none other than Archimedes himself, one of the famous mathematicians. Here's what he says. The shortest distance between 2 points is a straight line. That leads us into the idea of the Pythagorean theorem. Hint, hint. Hopefully you already know it. If not, we'll talk about it a little bit later in the class. And if you think about it, linear equations remind us that simplicity is the best root. And what it means by linear is that there's no power bigger than 1. I mean, it's super, super simple. And so we've got a couple formulas we talk about. For example, slope-intercept formula. Say it in 3, 2, 1. Y equals mx plus b is the correct answer. What does our m represent? That's our slope. What does our b represent? That's our y-intercept. Very good. Standard form, don't use it as much. Ax plus by equals c. Every time we see a standard form, we usually just convert it right over back to slope-intercept form. Unless they're asking us for x and y-intercepts, which we'll talk about here in a moment. But, for example, in number 67, they give us an equation and they say, find the slope and y-intercept. Well, I look at this bad boy and I'm like, this looks like standard form. Standard form is disgusting, so let's force this to be in slope-intercept form. To do that, we really just need to get solve for y, get y by itself. And so 2y is equal to -2x minus 10. Divide everything by a bunch of 2's, and we get y equals -x minus 5. From there, the slope is a hidden -1. So I can say m equals -1, and my y-intercept is a -5. And that's what it asked me to do. It says identify the slope and y-intercept. Well, there they are, right there. We're done, okay? You do the exact same thing for 68, just get different numbers. On number 69, identify the x and y-intercepts. Here what we're going to do is to find an x-intercept, we're going to set y equal to 0 and solve for x. And to find the y-intercept, we're going to set x equal for 0 and solve for y. It's kind of this cool inverse relationship. So I'm going to do the x-intercept first. To find that, I plug in a 0 for y. When I do that, I get 4x minus 0 is equal to 8. Don't even have to write that. 4x equals 8. Let's divide both sides by 4. And I get x equals 2. That's our x-intercept. We also call that a 0. So we crossed the x-axis. Y-intercept, I plug in a 0 for x. And so when I do that, this all goes away. And so I'm just left with negative y is equal to 8. I can divide both sides by -1. And I get y is equal to -8. That is our y-intercept. That's it. Same thing for 70, doing it really, really quick. To find the x-intercept, plug in 0 for y. 6x is equal to 60. X equals 10. To find the y-intercept, get rid of x. Plug in a 0. 6 times 0 is 0. 15y equals 60. Divide both sides by 15. It should get y equals 4. Yep, that's right. And there's my y. There's my x-intercept. Very good. 71, graph the linear equation. To graph an equation, you need 2 things, okay? You need the slope and your y-intercept. I can look at this equation and I can figure out the slope. The slope is 5, and the y-intercept is -3. So let's actually plot that point, -0, -3 is the official point. And then I go up 5 over 1. 1, 2, 3, 4, 5 over 1. And then I'll go down 5, 3, 4, 5 over 1, okay? Here's my line. Let's see if I can draw it nice and straight. Boom, boom, boom. We are done, okay? 72, they give you in standard form, convert it to slope-intercept form, and then graph, okay? 73, convert all of these to slope-intercept form. Find which one matches a y-intercept of -2 and a slope of -1, 2, 3, -3. So a slope of -3 and a y-intercept of -2, and then you're good. 74, same thing. 75, same thing. 76, graph the equation. This is a good problem. This test that one day where we talked about vertical and horizontal lines. Any form of the line x equals a, so x equals some number, is going to be a vertical line. Okay, so in this case, x equals -1 is going to be a vertical line on x equals -1. Why? Well, what's the x value of every single one of these points? What's the x value? It's always -1. That's why that's the line. The y value, you guessed it, you're going to have a line at y equals 4. It's going to be a horizontal line. Why? Funny question. Why? Well, because the y value is always -4. 1, 2, 3, 4, 1, 2, 3, 4. At every single value, it's -4, or it's +4. So that's why it's y value. Topic 11, can you write me a linear equation given a point and slope or 2 points? And this one, I got a quote from none other than Mr. Albert Einstein. And here's what it says. If you can't explain it simply, you don't understand it well enough. And I'm not really seeing the connection here between what AI wrote me. Here's what AI says. It says, writing equations is math's way of simplifying and explaining relationships. Not a single one of those words talks about a point and slope or 2 points, but you know, we'll let AI go on that one. First off, we need to know point slope formula. This is something I would definitely memorize. It will be on your semester exam, so I hope you took note of that. And it's this: y minus y1 is equal to our slope m times x minus x1. Okay. Given a point, given a slope, we can write an equation in point-slope form, hence why it's named that. And so in number 77, they actually begin to talk about, here's a point, here's a slope, write me an equation. And so let's actually do that. Well, y minus y1, what's my y coordinate? It's a 9. Y minus y1, y minus 9. It's equal to our slope times x minus x1. Okay. From there, we don't really care for point slope form. I mean, I like it, most people don't. So we're going to actually put that into slope intercept form, okay? So I'm going to have y minus 9 is equal to -4x plus 2 minus 8. Add 9, boom, 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 boom. I get y equals -4x plus 1, and we are done. I took it from point slope form, and I wrote it in slope intercept form, okay? Same thing for 78. What if they throw you a curveball and they give you 2 coordinates of 2 points and they say, well, write me an equation in slope-intercept form? Okay, well, I don't have a slope, but I have a y-intercept. What are we going to do? Great question. Well, if they give me 2 points, what can I find? I can find a slope. Once I have a slope, do I have a point? Sure. Once I have a point and a slope, can I write an equation in point-slope form? Sure. Once I have an equation in point-slope form, can I write it in slope-intercept form? You betcha. And so that's what they do on 79 and 80, okay? Now let's move over to parallel perpendicular lines. This shows up quite a bit in geometry. You learn some cool theorems about these there. But the fun topic we have here is, again, from an unknown person. So, again, Mr. Bivens came up with this. Wink, wink, cough, cough. Not really. And here it is. Some paths cross, others run alongside. But every line has its purpose. And you can believe that parallel and perpendicular lines have their purpose. And that's a great quote from AI there. But talking about slopes of parallel lines, they have the same slope. 2 lines that are parallel must have the same slope, meaning they will never intersect ever, ever, ever. Slopes of perpendicular lines, they have opposite reciprocals. Or negative reciprocals, whatever. In geometry, we teach it that the slopes of 2 perpendicular lines must multiply to -1. Meaning they must be inverses. Okay, think back to our properties earlier. Everything's so connected. Okay, so if I ask you to write me an equation of a line in slope-intercept form that's parallel to another line, well, we need to know about this line. What is the slope of this line? And if this other line is parallel, well, it's got to have the exact same slope. So we need to know the slope of this line. To do that, let's convert it to slope-intercept form. So let's subtract the 3x over. I'm left with negative 2y is equal to, let me zoom in here. Negative 2y is equal to negative 3x plus 8 divided by negative 2 everywhere. And I have y is equal to 3/2 x. 8 divided by negative 2 is a positive 4. Nope, negative 4. Good catch. And my slope here is 3/2. And so all I need to write is another equation that has a slope of 3/2 x that has a different y-intercept. And so I'll pick, in this case, 3x plus 30. Why not? It has a different y-intercept, and so those lines are parallel. So there's my answer. And you could put a multitude of answers. You could put plus 28, 27, 65. The only answer you couldn't put is 3/2 x minus 4. If you put that, you're wrong. Those are the exact same lines. Okay. Same thing for 82. In this case, you're looking for line perpendicular. So instead of replacing, once you actually solve for this slope, you wouldn't use 3/2. You would use a negative 2/3, which is what we actually call the opposite reciprocal. So the reciprocal, you flip the fraction, and then you negate it, or you make it negative. So negate, that's geometry, not algebra. 83 and 84, very similar. You find the slope of a line, you write an equation in point slope form, and then you just convert it back to slope intercept. 2 topics left, almost done. Looking at the line of best fits in linear regression. This is our little statistics world. And so it asks us in number 85, pause, didn't do our quote for topic 13. And here's our quote. This is by Vince Lombardi, the Lombardi Trophy for any of my football fans out there. I think it's football at least. Here's what Vince says here. Perfection is not attainable. But if we chase perfection, we can catch excellence. I don't know about y'all, but that speaks to me. That just hit my soul. We can't be perfect in everything we do, but we can do as good as we freaking can, okay? And so his example in that is that a line of best fit's not perfect, but it captures the overall essence of the trend, or all these points. For me, to do these, find the scatter plots, 2x plus 1. On number 85 here, what I'm going to do is I just kind of generally look, okay, what line looks like it fits this, okay? Which one of these look like they have a slope of 2? Okay, well, not C, that's a negative slope. Not D, that's a negative slope, so it can't be either of those. So it's either A or B. Let's see, let's just pick 2 points, pick this point and pick this point. I go up 1 over 2, that's a slope of 1/2, so it can't be A. So the only option I have left is B, okay? So the answer has got to be B here. It has the closest to a slope of positive 2. Okay. 86. These are our favorite problems ever to do. This is, again, we're going to use our calculator for these. But because I see this word year, I'm actually going to change some stuff up about my data. I'm not going to plug all of this in to my calculator. Let's change our 2002, change our first year to 0. And then we say how many years have passed since that first year. Well, 1 year's passed, 2 years passed, 3, 4, 5, 6, 7, and 8. Okay. And so at 8 years passed, we've got some example. And so let's actually plug this information I'm about to highlight in yellow into our calculator. Okay, and I'll go ahead and show you that now. Boom, boom. We go to stat. We click edit. That's not edit. We click edit. Let's enter in our years. So year 0, 1, 2, 3, 4, 5, 6, 7, 8. And let's go over and enter our y values. I have 34, 45, 42, 53, 58. And again, I'm just putting these values into my calculator, and then we're going to have our calculator do some actual math with it, okay? 47, 57, 65, and lastly 59, okay? Once we've put our information into the calculator, we're going to hit stat, we're going to hit calc, and we're going to hit 4. And just spam the enter button a whole bunch until it gives you some data, okay? They give me a equation in slope-intercept form, our favorite form. And it says this y equals ax plus b. Our a is our slope, our b is our y-intercept. Let's take that information and let's actually go solve some problems with it, okay? So the equation it gave me was y equals 3.0, and I'm going to go and round, 7x plus 38.8. And then let's go actually get some information about the problem. A campground keeps a record of the number of campsites rented, blah, blah, blah. Use the equation to predict the number of campsites rented in 2020, okay? Well, 2020 is how many years away from 2002? 18 years, so I'm actually going to plug 18 into my x value, okay? That's all it's asking. It's asking to find the number of campsites. What is that? That's my y value. It says find y. Sometimes they give you y and say find the x. In this case, they say figure out the number of campsites. Here's my x, here's my y. It says find the number of campsites. 2020 is 18 years away from 2002, so I'm actually going to plug in 18 into my x value. Let's change colors. Y equals 3.07 times 18 plus 38.8. Again, throw that in a calculator. You should get about y equals 94 campsites. And you're done. Okay, and I just, again, threw this whole thing in my calculator. Okay, in my calculator brain. That's scatter plots. Moving on to the last topic of our exam. We just had a quest over this, and y'all crushed it. I think fourth block had an average 98. Third block had an average of 96. Phenomenal exam average there. And again, we have another quote by Einstein to summarize this topic. And here's what it says. In the middle of difficulty lies opportunity. Direct and inverse variations are opportunities to understand how different things actually relate dynamically. And so I'm going to give you, kind of fill out this chart here, if you haven't already got this, to just kind of recap what direct and inverse variation is. We had a cool story on direct Dave and inverse Ivy. Direct Dave said that one thing goes up, another thing goes down. That looks like an equation of y equals kx. Ivy said things had an inverse relationship. One thing went up, another thing went down. And that looks like y equals k divided by x, where k is our constant of variation. We find those a lot. Graphically, direct variation just has to go through the origin. That's pretty much it. Indirect variation, basically they kind of opposites. They kind of mirror each other. So for example, I could take this and I could flip it over here. If that's the truth, then it's true. It could also be in these two quadrants, but that's just a generic kind of graph of them, okay? Their relationship, a direct variation has a constant ratio. Okay, and to find that ratio, we actually take our y value and divide it by our x value. So I think direct divide. Inverse variation, we have a constant. Any guesses? Product. Boom. We multiply. And so I actually am going to multiply y times x. Or x times y. Doesn't matter what we multiply. Okay. Example number 87. Let's see, determine which of these, if they represent a direct or inverse variation. And then from there, write me an equation. Okay. And so just looking at these numbers, it doesn't really give me direct variation vibes. You could check it. You could take y and divide it by all the x's. Negative 8 divided by 2 is a negative 4. Negative 4 divided by 4 is a negative 1. So it cannot be direct variation. But what if we multiply these numbers together? 4 times negative 4 is negative 16. Negative 16, negative 16, negative 16. So probably check this and throw in a calculator. Beep, beep, boop. And yeah, looks like negative 16 to me. So it's going to vary inversely. What's my constant? Well, you take your y multiplied by your x, you get negative 16. And if I want to write an equation, it's going to look like y equals whatever that constant is divided by x. There we go. Okay, pretty much it. Same thing for 88. This one's going to end up being a direct variation. Your constant should be 1/3, and your equation should look like y equals 1/3 x. Okay. These, again, using very similar things. There's really not too much direct inverse variation. If it varies inversely, you can multiply. So negative 72 has to be equal to 5y. You get y equals negative 14.4. Okay, y'all can solve these pretty well. If it varies directly, you're going to divide. So you'll set up a proportion, cross multiply, you'll solve. You'll get x equals 7 here. It's a weird 7. X equals 7. Okay. This one, whatever comes first is your y. Whatever comes next is your x. If 8 gallons of gas are used to drive 204 miles, how many miles can you drive 18 gallons of gas? So I'll set up in a proportion. It looks like 204 over 8 is equal to y over 18. You'll solve. You'll get y is equal to 459 miles. And then you'll do the same for 92, except that case it will be inverse variation. 4 times 21 equals 12 times y. You get y equals 7 hours, okay? Thank y'all very much. There's the test right below. Boop. Only showed you a little bit. If y'all have any questions, feel free to email me. Looking forward to seeing how well y'all do. And Mr. Bivens signing out.